Just an overview. First thing we'll go over waves, then we'll go over excited and ground state, then we'll go over electron configuration, noble gas configuration, Lewis dot structures, and then our pre-AP extension. Okay, so first things first, we have our wavelength and our frequency. So wavelength is the distance from one point on a wave to the same point on another wave. And when I say another, I mean like the next wave. So then frequency is the number of waves in a unit of time. So then we have two pictures, okay, down here. And we have one that has a high frequency and a short wavelength. So as you can see, we have like 20 waves, I'm not actually counting, in this picture. And you can see that the waves are really small. And then in the same amount of space here, we have 1, 2, 3, 4. We have 4 waves. And you can see that the wavelength is much longer. Okay, so question is, as the frequency of the wave increases, what happens to the wavelength? So here's a really good example. So we increased the frequency and you can see that the wavelength decreased. That means you have an inverse relationship. As one goes up, the other goes down. Okay, and so it asks, as the wavelength increases, okay, so now we have wavelength versus energy. So if you remember when you were doing the lab and you had to make more waves, so we had a lab where you were given a rope or a slinky or whatever, and to make more waves, it took more energy, you physically had to put in more energy to make the waves, to make more waves. So as your wavelength increases, the amount of energy is going to decrease. Okay, so here is your EM spectrum. Your gamma rays are your highest energy waves, and they have the shortest wavelength. Then it goes to X-rays, ultraviolet. Then you have your visible light, which is right in the middle. Invisible light is the light you can actually see with your eyes. Okay, then it goes to infrared light, microwaves, like the microwaves in the microwave that heats up your food. And then you have radio waves, which is like the radio waves that go to your car. Okay, so now we're talking about excited versus ground state. So if you remember, we did our flame test lab and we took our flame and we put it in the fire. Okay, when you put it in the fire, that heat from the fire was energy being added to our atom. And what that did was it took our electron and it moved it into the excited state. However, you can't leave your electron in the excited state. It's eventually going to go back to where it originally was, in ground state. And when it does that, when it goes from excited state to ground state, light is released. And so that's really important. From excited state to ground state is when light is released. Electron configuration. So the first thing we're going to look at is we're going to look at our actual how electron configuration is written. So the first thing that's talked about is our energy level. And so when we're talking about energy levels, you need to think of that as the rings around your nucleus. So you have your nucleus right there, and then you have your first ring, and then you have your second ring, and your third, and your fourth, and your fifth. Atoms don't look exactly like that in practice, but that's a really good way to think of it. And so that's the very first number that you're going to see. Then you have your sublevels, and your sublevels are broken up nice and easy on our periodic table right here. So we have our first two rows, there are S sublevel. Then in the middle of our periodic table is our P sublevel. And then, or not our P, our D sublevel, I'm sorry. And then we have our P sublevel is on the far right side. And then down here at the bottom is our F sublevel. And then this number right here tells you how many spaces are either in that element or in that sublevel, or how many spaces you're counting over in that sublevel. Okay. So now we're going to move on and we're going to look at carbon. Okay, so carbon is right here. This is our first guy right there. So we're going to, whenever you're doing electron configuration, you always start from hydrogen. Okay, so hydrogen is in 1s. And so we want to get from hydrogen to carbon. So we're going to go and we're going to say, okay, 1s. Now we have hydrogen and helium. There are two elements in that 1s section. So we're going to have 1s2. Then we move on to 2s. And so we have 2s and we have two elements in 2s. We're still not to carbon yet. So we have 2s2. Then we get to 2p. Carbon is in 2p. So we're going to count from where carbon is. We're going to count to see how far over carbon is. So we have boron is 1 and then carbon is 2. So that's how we got 2p2. Okay. So now we're going to move on and we're going to look at zirconium. So zirconium is right here. It's number 40 on our periodic table. And again, you start all the way back at hydrogen and then you go and you just read the periodic table as you go. So you start out, you have 1s and there's two elements in 1s. So 1s2. Then we have 2s. There's two elements in 2s. 1, 2. So we have two electrons. That's where our two electrons go. 2s2. Then we have 2p, and in 2p we have 1, 2, 3, 4, 5, 6 boxes. So that's, we're going to put a 6 at the top. Then we have 3s2, 3p6, 4s2. Then we have 3d. The D section is always 1 minus 1 of your row of the energy level that you should be on. One thing you should also remember is that your energy levels correspond to the periods or rows on your periodic table. So we have 3D, 10, and then we have 4P6, 5S2, and then we have 4D, and zirconium is the second one in 4D, so we have 4D2. Okay? Now, one thing I want you to do is I want you to go through and I want you to write your stuff for sulfur and gallium. Okay? Thank y'all so much for doing that. You can type in your answers here, and there is our answers for our sodium and our gallium. Okay, so now one thing that I always hear my kids complain about is like, Coach Martin, these are so long, they're so long. And so there is a shortened way, and the short way of doing this is we are going to write it in something called noble gas configuration. I apologize, I didn't put this on our slide. But we have noble gas configuration. And I don't know if you remember this, but our noble gases are our very last row on our periodic table. And in our next unit, in one of the next units, we're going to learn about why noble gases are so special and why we use them all the time as a reference point. But how you do noble gas configuration is you find your element, and in this case we're going to do carbon, and you're like, okay, so I have carbon, and then you go to the noble gas, which remember is this row, the right row, the noble gas before whatever element you're talking about. So for carbon, you're going to go up and you're going to go over, and the noble gas before carbon is helium. Okay, then helium takes the place of everything up until you get there. And then you write everything that's on the same row as the element that you have. So in this case, that's going to be 2s2 and then 2p2. Okay? Then we have our zirconium. Okay? We have our zirconium. So we go to our Z, and then we go up and we go all the way over to our very last row. and our noble gas that's before zirconium is krypton. Okay, so that goes in brackets here. And then you write everything that's on the same row as your element. So we have 5s2, then we have 4d2, and that brings us to zirconium. Okay, again, I'm going to give you a chance to go and do your sulfur and your gallium noble gas configuration. Okay, here are our answers for that. So we have for sulfur, you go to your sulfur and then you go up and over, and there's our neon. And then you write everything for sulfur, which is 3s2, and then we have 3p1, 2, 3, 4. And that's how we got that one. Then we have our gallium, which is right here. It's on our third row. We go up, we go all the way to the right to argon, which is our noble gas before gallium. And then you write everything in that row that gallium is on. So you have 4s2, 3d10, and 4p1, because gallium is again right here. Okay, y'all are doing a great job. Okay, so now we are moving on to orbital diagrams. We're moving on to orbital diagrams. And so we're going to go through the rules and then we're going to see how they look. So basically a picture representation of our electron configuration that we were just doing. And so you have arrows that represent electrons. You have your sublevels set up, and I'll show you a more detailed picture of that in a second. But you have three main rules. Your first rule is Aufbau's principle, which means that when you're filling up an orbital, you want to make sure that all of your orbitals are filled before you move on to the next one. So for example, you have 4 electrons here, and you can't skip one. So you see how this one is skipped? You can't do that. You have to make sure that all of your orbitals are filled before moving on to the next one. Okay, then we have Hund's rule, and this is fill in all of your single orbitals before doubling. So what that means is if you have if you're in, this is our D sublevel, okay, because we have 5 different spaces. If you have 5 spaces, you want to make sure that you have 1 electron in each space before you start to pair up.